Hello friends and welcome again. Today we'll be talking about shallow foundation design, specifically pad footings. There's three aspects to the shallow footings design. And the first one is being a bearing capacity check, which is a design function that is related to the capacity of the soil to take your compression loads without actually failing. And when we say failing in geotechnical aspect, it doesn't mean complete collapse down because that rarely happens, but the bearing settlement failure is actually where there is too much settlement below one end of the footing that it starts to rotate and fail. That sort of rotation that is created because of the soil settling a lot below the footing can just result in cracking in the building, and the doors may not be able to open and close again, or you might have the windows making noises and moving at night and things like that because they're just not vertical anymore because the footings have rotated. And it could be somewhere catastrophic because the footing has rotated, the structure is no longer vertical. That generates a lot of lateral loads on the building that it was not designed for, and you might start having some big problems in the building. Hopefully it doesn't collapse. But something like the Leaning Tower of Pisa, for example, if you can think about that, it's a typical example of a geotechnical failure. Not a structural failure, a geotechnical failure, because the soil has sort of compressed below the tower on one end, and the whole tower just rotated from its vertical plumb. So that's the first thing we check for, and then we're gonna do the structural check for footings that involves a typical slab design, which you would usually check for bending, shear, and punching shear. And then we're going to look at the detailing of the structure afterwards. So first, let's look at what's a pad footing. As you can see in this picture, this is a real pad footing reinforcement before the concrete is poured. And it's basically just a concrete on top of the soil to spread the load from your columns into the soil. Your columns can typically take quite a bit of compression load because concrete is quite strong, but the soil not so much. So you need a bigger area of concrete just to spread the load from your columns onto the footings. In terms of design, we'd refer to the width of the footing with a capital W letter and the length of the footing with a capital length letter. So first, let's look at the bearing capacity of the soil. And the allowable bearing capacity is usually given to you by the geotechnical engineer after he investigates the soil and do a few lab tests on the soil. And the design check that we need to do here is that we need to check that our service loads coming down onto the footing divided by the area of the footing, which gives you a pressure. So this is the applied pressure from the building onto the footing, onto the soil, is actually less than this allowable bearing pressure limit given to you by the geotechnical engineer. Typical values for this can be around 50 kPa. That is the absolute minimum. If you're not sure of the soil, it would be safe to assume 50 kPa, but that would be too conservative. Stiff clays and sandy soils can go to about 250 kPa. If you have loose rock or weathered rock, you can expect about 500 to 700 kPa. You can expect around 1000 for moderately weathered rock. And for very stiff rocks and dense rocks, you can expect something like 1500 kPa. And obviously, the deeper you go from the ground level, the better the soil capacity that you can have. So, a tip for design here, if your building has a basement, chances are you're gonna be going into a stiffer soil. So chances are your actually footings might work better. So to recap here, you work out your service loads from the building and you have your allowable soil bearing capacity from the geotechnical engineer. Then you can work out what is your length and width of the footing that is required. Now, what if you run into a situation where the area required is just ridiculously large, something like 8 meter by 8 meter or 10 meter by 10 meter? It's basically taking the whole grid between the columns. And when you encounter this situation, it straight away should trigger you to think that maybe using a shallow footing is not the correct decision to go for over here. Maybe we need to go for a deeper footing. maybe we need to go for a piled foundation, or maybe we need to excavate deeper and put our footing on a deeper soil. Depends on how far down is the nearest soil. If you're only about 1 meter above a stronger soil, maybe it's worth it to actually excavate extra 1 meter and make your footing deeper so it sits on a stiffer soil. But if your stiffer soil is something like 5 to 6 meters, it's too much to excavate for it. And in this case, it might be more worth it to actually go for a board piers foundation, a piled foundation. The second option is to consider actually using a raft, which we're gonna see in a minute. A raft is actually a huge pad footing, but this option is really viable to consider a raft if you have a column with a huge load and the column nearby only has a much less load. In this case, a structural raft can take your loads and spread it into a much bigger area than your pad footing, and maybe using the raft is a good option over here. A final tip here when you are checking for your geotechnical capacity is to take into account your live load reduction. If you're not sure, live load can usually be reduced by up to 50% for residential loads, office loads, hotel loads. If you have any of these loads on your building, especially the higher the building is, the more benefit you can actually get from using this live load reduction, because you're more likely that you're going to be able to reduce it by up to 50%. Now let's look at our footing structural design. A good tip that's just going to make your life much easier, if you can imagine this footing reversed. So what that does is that you have the soil pressure applied as a UDL on your footing, which we can also think of as a slab or as a beam, and your column is your support. The moment you do this simple visualization, the design becomes much easier. Also, another thing to be careful of is when you're doing this structural design, be careful to be using the ultimate loads and not the service loads. We check the bearing capacity with service loads, but we design the structure to ultimate loads. So we have to work out the ultimate soil pressures, and then from there, we can treat that as our UDL on the slab, or our load on the slab. And from that point forward, it becomes much easier. You can straight away analyze your bending moments as a double cantilever. You have a cantilever either side. You have your UDL on the slab, and based on that, you can straight away work out your moment at the design section. And just like any slab, according to the Australian standard, you take your design action at about 0.7 of a support from the center of the column. And a support is basically half the width or the length of the column, depends on the direction you're designing in. So in this case here, if we assume that the column length is actually L, our 0.7a is actually 0.15 L. And if we substitute that into the equation, we can work out that our design location of the critical bending moment to design for is actually half L minus 0.35 L. And once we work out that location, we can straight away work out our design bending moment, which is our design pressure times by the distance, just like a cantilever, squared divided by 2. Now we gotta repeat that for the two directions, because we're designing in the length direction and in the width direction. Similarly, for the shear design, we know that our critical shear is always taken at a distance of d0 from the face of the support, which is basically L over 2, which is half the support length, or the column length in this case. Once you know your critical shear location, again, just like a cantilever, if you want to work out how much is your shear force at this distance, what you gotta do is you multiply your design pressure times this distance. Last check we have is the punching shear. Again, just like a slab design with punching shear, you gotta work out your punching shear perimeter, which is this one over here. And this is equivalent to the length of the column plus your DOM over 2 either side. So we take DOM over 2 here, and we take DOM over 2 here, and this is our length of the column. And we do it again in the other direction with the width parameter. So we end up with this area over here, which is my along the punching shear perimeter. And because this area is always excluded from the load that's causing the punching shear check, because if you actually think about it, any load that's within this area goes into direct compression. It basically goes directly through your pad footing or your slab, and it doesn't cause a punching failure. Only the load outside of this punching shear perimeter area is the one that causes your failure. So whatever your design load was, in this case it was Q ultimate, that one is going to have to be multiplied by the big area, which in this case is length by width of the pad footing, but we're going to take out the area of the punching shear because we agreed that it's just going to go into compression. It's not going to cause you punching failure. And this area is basically your L plus DOM multiplied by your width of the column multiplied by, plus DOM. And basically this is the punching area, and this is the whole pad footing. And the difference between the two is the area that causes punching failure. Alright, so we've got that load in, and we have this equation over here to work out our design punching shear. So to recap here, we've got our critical design moment, we've got our critical shear force, and we've got our critical punching shear. Now we have the design actions. All what we have to do is design the footing using the slab design to the code that you're designing to. And you basically treat it exactly like a slab. One very helpful tip to mention here is that always keep in mind that you're going to be designing in two directions for your pad footing. So when you're sizing up the pad footing initially to achieve your allowable bearing pressures, try to always keep the distance from the face of the column to the end of the footing the same in the two directions. This way, your bending moment and shear force in the two directions is going to be the same. So you actually need to design it only once, and you can simplify your life a lot. Also, you will often find that if you have a very good soil, your design is going to be governed mostly by punching because you don't need a big footing and your span is just quite short. Your moment is very small. What governs is often your shear and your punching capacity. So always try to keep your footing depth to a minimum first, let's say 400 depth, and start increasing the concrete grade. Let's say 32 MPa, 40 MPa, 50 MPa, and even 65, because it's easier to use a higher concrete grade than to excavate deeper. There's bigger risks that comes with excavating deeper. Especially if you go deeper than 1 meter, the safety concerns start to become bigger because the soil might just collapse when they excavate. So always keep in mind that you can manipulate the concrete grade first and then manipulate the footing depth if you need to get your shear to work. If you have a soft soil and you end up with a big footing, then your design is going to probably be governed by bending because of the long span. And in this case, the depth doesn't help you as much. Working with 400 or 600 deep footing is probably good enough for bending, and you'll just need to keep increasing your reinforcement until you can achieve your bending capacity. Now let's look at the detailing of the footing. So according to AS 3600, which is the Australian code for designing concrete structures, you have two options for footing design. You can actually design the footing as unreinforced, or you can design it as a reinforced footing. First, let's look at the reinforced footing. Probably it's quite simple. You design it exactly as a slab, which is section 9, and you provide a minimum reinforcement of 0.19 D on D square FCTF FSY, which is over here. And basically, that is just straightforward like a slab design. A question that often comes up, then, do I need to cog my bars at the end of the footing, as you can see over here? And the answer is, it depends. Because if you recall, our bending moment looks something like this. And because of this, our critical section was taken somewhere along here. Maybe by the time you reach this location, your moment is very minimum. You basically don't need reinforcement anymore. So whatever that distance is, you actually got to work out if this is enough to develop your length. If it's enough to develop your bars and tension, then you don't need to cock the bars. But if it's not enough to develop your bars and tension and you need that extra 50% capacity when you cock the bar, then you need to cock the bar. Now let's look at unreinforced footing design, and the general requirement is that it needs to be 200 mil deep as a minimum, and when you're designing the section you need to take 50 mil less than your depth. So for example, if you had a 600 footing, instead of taking 600 in your design, you should just take it as 550. And basically the code does that just to allow for the fact that the lowest 50 mil of concrete is just not gonna be even, and it's not very reliable because it's just poured against the soil pretty much. And then you work out your strength in bending, and what it asks you to do is that you're gonna take your bending capacity based on your characteristic flexural strength, which as we know is 0.6 times the square root of the concrete grade that you're using. And because concrete cannot be assumed to have plastic behavior when it's under tension, in fact it's just gonna snap, we are gonna have to assume an elastic stress diagram like this, where we have our compression at the top and we have our tension at the bottom. But because it's elastic, it actually has to be balanced. So the force at the bottom here is going to be equal to the force at the top, and basically this distance between the two is your depth of the footing minus 50 mil as required by the code, and that is your lever arm. And this peak stress is basically your 0.6 square root FC dash. You work out with a safety factor of 0.6, and based on that you can work out what is your bending capacity as unreinforced section. Secondly, for shear, you can also work out straight away the shear capacity of the section. Again, don't forget to apply your safety factors here. And for punching shear, it's the same thing over here. This is exactly the same equation as the punching shear equation. The only difference is that this factor over here is taken much more conservative to reflect the fact that it's unreinforced. Generally, if you have a very stiff soil, let's say you are building a building that has 2 or 3 basements and your footing is somewhere about 10 meters below the ground, you are already sitting on a very strong soil, perhaps even rock, and you find that you don't need a big footing. So your footing is literally just maybe under a meter by a meter, and it's supporting huge load. But because the soil is so strong, it can take such a big pressure, you find that you don't need a big footing. And because your footing is not big, your design forces is almost zero. Because as we've seen over here when we were looking at our structural design, maybe your footing is actually very short, that this distance over here ends up being outside of the footing. And maybe this distance over here and this moment is just so small because instead of being here, maybe it's actually here. Because your footing is just not big, it's just very small. So your design action and your punching shear perimeter, instead of being around here, maybe it's actually outside of the footing. So punching is not even going to happen in your footing. And because that is the case and you don't need the footing to be reinforced, the code recognizes that and gives you the permission to actually design it and it's unreinforced and just have the concrete thrown in. Some people don't feel comfortable with relying on the concrete flexural strength to actually achieve the capacity in bending. That's fine. You can just add enough reinforcement in at the bottom to just take that bending capacity, but you don't really need to. By the way, if you're interested into going deeper into lateral loads analysis and design, as well as modeling a complete full building on the finite element analysis software called ETABS, you can check out the links in the description of the video below. There is a full course that I've prepared on Udemy, and you can access it with the link below for a heavily discounted price. I hope that you find this video quite helpful. Don't forget to subscribe to the channel and keep an eye in the upcoming weeks for the videos that will be released on the design of the shallow, deep and high parade footing foundation.